Tonight, we're going to explore something you encounter every single day. Something so ordinary you barely think about it, yet so deeply strange that physicists are still arguing about what it actually is. Light. Specifically, the thing that makes light. The photon. Here's what makes this so mind-bending. A photon has no mass, yet it carries energy. It travels at 300,000 kilometers per second, yet from its own perspective, it experiences no time at all. It can behave as a wave or a particle depending on how you look at it. And somehow, a single photon can interfere with itself, as if it travels through two places at once. By the time we're done tonight, you're going to understand why Einstein called the photon the most mysterious thing in physics, and why that mystery only deepens the more we learn. Before we dive into the quantum strangeness, if you find this kind of deep exploration interesting, a quick like or subscribe would really help the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems obvious. You turn on a lamp and light fills the room. You step outside on a sunny day and light warms your skin. You look up at night and see stars that have been shining for billions of years, their light finally reaching your eyes after crossing incomprehensible distances. Light seems simple. It's just there, illuminating the world, letting you see, making life possible. We swim through it every waking moment without giving it a second thought. But here's the strange thing. For thousands of years, humanity had absolutely no idea what light actually was. And even today, after centuries of scientific investigation, after quantum mechanics and relativity and the most precise experiments ever conducted, light remains one of the most bizarre phenomena in the universe. The more we learn about it, the stranger it becomes. The photon, the fundamental particle of light, behaves in ways that seem to violate common sense, that challenge our basic assumptions about reality, that forced physicists to abandon intuitions that had served humanity well for millennia. This is the story of how we discovered what light really is, and why the answer is so much weirder than anyone expected. The ancient Greeks had ideas about light, of course. They were the first civilization to seriously investigate natural phenomena through reason rather than mythology. Plato thought that light emanated from the eyes, reaching out to touch objects and allowing us to perceive them. In his view, vision was an active process. Your eyes sent out rays that interacted with objects and returned information to your mind. This sounds absurd today, but it matched certain intuitions. We talk about casting a glance at someone, as if our gaze has physical force. We say that someone's eyes lit up, as if light originates in the eyes themselves. Plato's theory was wrong, but it captured something about the subjective experience of seeing. Aristotle disagreed with his teacher. He believed light was a disturbance in the medium between the eye and the object, something like a wave traveling through air. Aristotle noticed that when you plunge a stick into water, it appears to bend at the surface. He recognized that light did something strange when it passed between different materials. He proposed that transparent substances like air and water and glass had the potential to transmit light, and that actual light was the activation of this potential. When you light a lamp, you activate the transparency of the air, and this activation spreads throughout the room instantaneously. Neither of these explanations was correct, but they set the stage for a debate that would continue for over 2,000 years. What is light made of? Is it a stream of particles? Is it a wave? Or is it something else entirely? something that doesn't fit into either category. For centuries, progress on understanding light was slow. The Romans, practical engineers that they were, used light without worrying much about what it was. They built lighthouses and used mirrors, and understood that light traveled in straight lines. Medieval Islamic scholars made significant advances in optics, developing lenses and studying how light bends when it passes between different materials. Ibn al-Haytham, working in Cairo around the year 1000, definitively disproved the emission theory of vision. He pointed out that if eyes emitted light, we should be able to see in the dark. We can't. Therefore, light must come from external sources and enter our eyes, not the other way around. But the fundamental question remained unanswered. What was this thing called light that entered our eyes from external sources? In the 1600s, two scientific giants offered competing theories that would dominate physics for centuries. On one side was Isaac Newton, perhaps the most influential scientist who ever lived. Newton believed that light was made of tiny particles, which he called corpuscles. These corpuscles, he argued, were shot out from light sources and traveled in straight lines until they hit something. This explained why light cast sharp shadows. Particles traveling in straight lines would create crisp boundaries between light and dark. Newton's corpuscular theory seemed to match what we observe in everyday life. Light travels in straight lines. It bounces off mirrors like balls bouncing off walls. It can be focused by lenses in ways that seem consistent with particles following curved paths. Newton published his theory of light in his Optics in 1704, and his reputation ensured it would be taken seriously. He had already revolutionized physics with his laws of motion and universal gravitation. He had invented calculus. When Newton spoke, the scientific world listened. On the other side was Christian Huygens, a Dutch scientist who proposed that light was a wave. Huygens argued that light moved through space as a vibration in some invisible medium, much like sound moves through air as a vibration. When you speak, your vocal cords vibrate, pushing air molecules back and forth. These vibrations propagate through the air until they reach someone's ear, where they cause the eardrum to vibrate, producing the sensation of sound. Huygens proposed that light works similarly. A candle flame or the sun would set up vibrations in some medium, and these vibrations would spread outward until they reached an eye. This wave theory could explain certain phenomena that Newton's particles struggled with. For instance, when light passes through a narrow slit, it spreads out slightly at the edges. This is called diffraction, and it's exactly what waves do. Sound waves bend around corners. That's why you can hear someone talking in the next room even though you can't see them. Water waves spread out after passing through a gap in a breakwater. If light did the same thing, maybe light was a wave too. For over a century, these two theories competed. Newton was so famous and respected that his corpuscular theory dominated, especially in England, where scientific patriotism favored the English genius over continental alternatives. But the wave theory had supporters too, particularly on the European continent where Huygens's reputation held more weight. The debate seemed impossible to settle. Both theories could explain some observations, but neither could explain everything. Each had advantages and disadvantages. Each had phenomena it handled elegantly and phenomena it struggled to account for. Then, in 1801, a British scientist named Thomas Young conducted an experiment that seemed to settle the matter once and for all. Young's experiment was elegant in its simplicity. He shone light through two narrow slits, side by side, positioned very close together, and observed the pattern that appeared on a screen behind them. If light were made of particles, you would expect to see two bright bands on the screen, one behind each slit. The particles would pass through either one slit or the other, and pile up in two distinct regions, like bullets fired at a wall with two holes. Some bullets go through the left hole, some go through the right hole, and you get two piles of bullets on the other side. Simple and intuitive, but that's not what Young observed. Instead, he saw a pattern of alternating bright and dark bands across the entire screen. Not two bright spots, but many bright and dark stripes extending well beyond the region, directly behind the slits. This pattern is called an interference pattern, and it's something that only waves can produce. To understand interference, think about dropping two stones into a still pond. Each stone creates ripples that spread outward in circles. Where the ripples meet, something interesting happens. If the peak of one ripple meets the peak of another ripple, they add together to create a bigger wave. This is called constructive interference. But if the peak of one ripple meets the trough of another ripple, they cancel each other out, leaving flat water. This is called destructive interference. The pattern Young observed was exactly what you would expect if two sets of waves were overlapping and interfering with each other. Light passing through the two slits spread out as waves, and these waves overlapped. Where wave peaks met wave peaks, you got bright bands. Where wave peaks met wave troughs, you got dark bands. The alternating pattern proved that light was behaving as a wave. Young's double-slit experiment seemed to prove conclusively that light was a wave. The corpuscular theory appeared to be dead. Particles don't interfere with each other. They don't cancel out when they meet. They just collide or pass by each other. Only waves create interference patterns. And Young had demonstrated that light creates interference patterns. Case closed. For the next 100 years, the wave theory of light dominated physics. Scientists developed increasingly sophisticated mathematical descriptions of how light waves behave, how they reflect off surfaces, how they refract when passing between materials of different densities, how they diffract around obstacles, and how they interfere with each other. The wave theory explained observations that the corpuscular theory never could. It seemed complete and beautiful. But if light was a wave, what was it a wave of? Sound waves are vibrations in air. The air molecules themselves oscillate back and forth, and this oscillation propagates through the atmosphere. Water waves are vibrations of water. The water surface moves up and down, and this movement spreads across the surface. What was light vibrating in? What was the medium that carried light waves? This question became increasingly urgent as astronomers studied light from distant stars. Light from the sun reaches Earth after traveling through 93 million miles of apparently empty space. Light from other stars crosses even vaster distances. If light was a wave, it needed something to wave in. But space appeared to be a vacuum, completely empty of matter. Scientists proposed the existence of a substance called the luminiferous ether, an invisible medium that permeated all of space. Light, they argued, was a vibration in this ether. The ether filled the universe, occupying every point in space, including the vacuum between planets and stars. It provided the medium through which light waves could propagate. The ether had to have some unusual properties. It had to be incredibly rigid to allow light to vibrate at such high frequencies. Sound waves in air travel at roughly 340 meters per second. Light travels at 300 million meters per second, almost a million times faster. For a wave to travel that fast, the medium must be extremely stiff, much stiffer than steel. But the ether also had to be perfectly transparent and completely undetectable, since we couldn't see it or feel it. And it had to be so tenuous that the planets could pass through it without any friction, since the Earth's orbit showed no sign of slowing down from ether resistance. These requirements seemed contradictory. How could something be stiffer than steel, yet offer no resistance to moving objects? How could something fill all of space, yet be completely undetectable? Still, the existence of the ether seemed necessary to explain how light could travel through the vacuum of space. Waves need a medium. Light was a wave. Therefore, there must be a medium. In the 1860s, a Scottish physicist named James Clerk Maxwell achieved one of the greatest intellectual triumphs in the history of science. Maxwell unified the seemingly separate phenomena of electricity and magnetism into a single theory. Before Maxwell, electricity and magnetism appeared to be distinct forces. Electric charges created electric fields. Magnets created magnetic fields. The two seemed related in some ways, since electric currents could create magnetic effects, and changing magnetic fields could induce electric currents, but the exact relationship was unclear. Maxwell showed that electric and magnetic fields are intimately connected, two aspects of a single electromagnetic field. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. The two are locked in a dynamic dance, each creating the other, each sustaining the other. When Maxwell worked out the mathematics of these interacting fields, he discovered something astonishing. His equations predicted the existence of waves, oscillating electric and magnetic fields that would travel through space at a specific speed. The electric field would oscillate, creating a magnetic field. The magnetic field would oscillate, creating an electric field. This self-sustaining oscillation would propagate forward, carrying energy through space. Maxwell calculated this speed from basic electrical and magnetic constants, quantities that could be measured in the laboratory using simple equipment having nothing to do with light. The permittivity of free space, which governs the strength of electric fields, and the permeability of free space, which governs the strength of magnetic fields. When Maxwell combined these constants according to his equations, the result was approximately 300,000 kilometers per second. This was almost exactly the measured speed of light. The agreement was too close to be a coincidence. Maxwell realized that light itself must be an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields traveling through space at the speed his equations predicted. He had not set out to explain light. He had been trying to understand electricity and magnetism, but his mathematics led him inevitably to the conclusion that light was electromagnetic radiation. This was a profound insight. It meant that light wasn't just something special and unique. It was part of a broader spectrum of electromagnetic radiation. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, all of these were the same fundamental phenomenon. They were all electromagnetic waves, differing only in their frequency and wavelength. Red light has a longer wavelength than blue light, roughly 700 nanometers compared to 450 nanometers. Radio waves have much longer wavelengths, measured in meters or even kilometers. gamma rays have much shorter wavelengths, smaller than atomic nuclei. But they're all electromagnetic waves, traveling at the same speed, the speed of light. The rainbow of colors we see represents just a tiny slice of this vast electromagnetic spectrum, the particular frequencies that happen to stimulate the receptors in human eyes. Maxwell's theory also solved the ether problem, at least partially. The electromagnetic wave didn't need a material medium to propagate. The oscillating electric and magnetic fields sustained each other. The wave was self-sustaining, requiring nothing but empty space to travel through. This was revolutionary. For the first time, physicists could imagine waves that didn't need a material medium. Maxwell's theory seemed complete and beautiful. Light was an electromagnetic wave. The debate between particles and waves appeared to be over, with waves as the clear winner. Textbooks were written. Courses were taught. The scientific community moved on to other problems, confident that the nature of light was finally understood. But at the turn of the 20th century, new experimental results began to emerge that Maxwell's theory couldn't explain. And these results would force physicists to reconsider everything they thought they knew about light. The first problem was called black body radiation. When you heat an object, it glows. A piece of iron, when heated in a forge, first glows red, then orange, then yellow, then white as it gets hotter. The color of the glow depends on the temperature. Cooler objects glow red. Hotter objects glow blue or white. This relationship between temperature and color is so reliable that astronomers use it to determine the surface temperatures of distant stars. Classical physics, using Maxwell's electromagnetic theory combined with the principles of thermodynamics, predicted how much light a hot object should emit at each wavelength. The calculation seemed straightforward. A hot object contains vibrating atoms and molecules. These vibrations should produce electromagnetic waves across a range of frequencies. The hotter the object, the more energy available and the more light emitted. But the predictions didn't match reality. According to classical calculations, hot objects should emit more and more energy at shorter and shorter wavelengths. As you calculated the energy at ultraviolet wavelengths, then X-ray wavelengths, then gamma-ray wavelengths, the predicted energy kept increasing without limit. A hot oven should emit infinite amounts of energy at short wavelengths. This prediction was so absurd that physicists called it the ultraviolet catastrophe. Obviously, hot objects don't emit infinite energy. Your kitchen oven doesn't flood your house with gamma rays. Something was wrong with the theory. In 1900, a German physicist named Max Planck found a way to fix the problem. But his solution was strange, almost desperate. Planck proposed that energy wasn't continuous, as everyone assumed. Instead, he suggested that energy came in discrete packets, which he called quanta. The energy of each quantum was proportional to the frequency of the light. High-frequency light came in large quanta. Low-frequency light came in small quanta. By assuming that energy was quantized, Planck could derive a formula that perfectly matched the observed spectrum of blackbody radiation. The ultraviolet catastrophe disappeared because at high frequencies, the quanta were so large that thermal fluctuations couldn't produce them. The theory fit the data beautifully. Planck himself didn't fully believe in the physical reality of quanta. He viewed his proposal as a mathematical trick, a computational device that happened to give the right answer. The idea that energy came in discrete chunks seemed too radical to take literally. Energy had always been treated as continuous, infinitely divisible, able to take any value. Surely the quantum hypothesis was just a calculational convenience, not a description of physical reality. But the idea of energy quanta was about to take on a life of its own. The second problem that classical physics couldn't explain was the photoelectric effect. When you shine light on certain metals, electrons are ejected from the metal surface. This effect had been known since the 1880s, when Heinrich Hertz first observed it while experimenting with electromagnetic waves. At first, the photoelectric effect seemed like it should be easy to explain with wave theory. Light waves carry energy. That energy should be absorbed by electrons in the metal, eventually giving them enough energy to escape the metal surface. Brighter light means more energy, so brighter light should eject more electrons with more energy. But the details didn't work out. According to wave theory, if you shone a dim light on a metal, it should take time for the electrons to absorb enough energy to be ejected. The dimmer the light, the longer it should take. The wave energy would slowly accumulate in the electron until it reached the escape threshold. But experiments showed that electrons were ejected instantly, no matter how dim the light was. Even the faintest light produced instantaneous electron emission. There was no delay whatsoever. Even stranger, the energy of the ejected electrons depended on the color of the light, not its brightness. Blue light ejected electrons with more energy than red light, regardless of how bright the red light was. In fact, if the light was too red, below a certain threshold frequency, no electrons were ejected at all, no matter how bright the light was. You could shine an incredibly intense red light on a metal surface for hours, and not a single electron would be ejected. But a faint blue light would eject electrons immediately. None of this made sense if light was a simple wave. A brighter wave should deliver more energy. A wave of any frequency should eventually deliver enough energy if you wait long enough. The color shouldn't determine whether electrons are ejected at all. But the experiments were clear. Something was fundamentally wrong with the wave picture of light. In 1905, a young patent clerk in Switzerland named Albert Einstein proposed a radical solution. Einstein took Planck's idea of energy quanta seriously. He suggested that light itself was made of discrete particles, each carrying a specific amount of energy determined by its frequency. These particles of light, which Einstein called light quanta, and which we now call photons, could explain the photoelectric effect perfectly. When a photon hits an electron in a metal, it transfers all of its energy at once. It's an all-or-nothing transaction. If the photon has enough energy, determined by its frequency, the electron absorbs that energy and escapes. If the photon doesn't have enough energy, the electron absorbs nothing and stays put. There's no accumulation, no gradual buildup. Each interaction is instantaneous and complete. This is why color matters more than brightness. Blue photons have more energy than red photons because blue light has a higher frequency. A flood of red photons, each with too little energy, will never eject an electron. It doesn't matter how many red photons you throw at the metal. Each one individually lacks the energy to free an electron, and the energy doesn't add up. But a single blue photon with enough energy will eject an electron instantly. Brightness determines how many photons hit the surface, which determines how many electrons are ejected. But each individual photon must have enough energy on its own. This explains why dim blue light ejects electrons but bright red light doesn't. The dim blue light has fewer photons, so fewer electrons are ejected, but each blue photon has enough energy to do the job. The bright red light has many photons, but none of them has enough energy individually, so nothing happens. Einstein's explanation was elegant and matched the experimental data perfectly. But it also seemed to contradict everything physicists had learned about light over the previous century. How could light be made of particles when Young's double-slit experiment had clearly shown it was a wave? The interference pattern that Young observed could only be explained by waves. Particles don't interfere with each other. They don't cancel out. They just pile up. This was the beginning of one of the strangest periods in the history of physics. Light seemed to be both a wave and a particle, depending on what experiment you performed. In some experiments, light behaved exactly like a wave, producing interference patterns and diffracting around obstacles. In other experiments, light behaved exactly like a stream of particles, ejecting electrons one at a time with discrete amounts of energy. How could this be? How could something be two contradictory things at once? A wave spreads out, occupying a region of space. A particle is localized at a single point. A wave interferes with other waves. A particle collides with other particles. These are fundamentally different behaviors. Yet light exhibited both, depending entirely on how you chose to measure it. This puzzle would occupy physicists for decades, and would eventually lead to the development of quantum mechanics. The most successful and most strange physical theory ever devised. And at the heart of this puzzle was the photon, the particle of light that somehow also behaved like a wave. Einstein received the Nobel Prize in 1921, not for his famous theory of relativity, but for his explanation of the photoelectric effect. The Nobel Committee recognized that Einstein's work on light quanta was one of the most important developments in physics. It opened the door to quantum mechanics. It revealed that the classical distinction between waves and particles breaks down at the fundamental level. But even as he accepted the prize, Einstein himself was troubled by what the photon concept implied. The quantum theory that his work helped create would develop in directions that Einstein found deeply unsettling. For the rest of his life, Einstein would struggle with the strangeness of quantum mechanics, searching for a deeper theory that would restore the determinism and locality that quantum mechanics seemed to violate. The word photon itself didn't appear until 1926, when an American chemist named Gilbert Lewis coined the term in a paper about the thermodynamics of light. Before that, scientists called them light quanta or radiation quanta. Lewis proposed photon from the Greek word phos, meaning light, and the name stuck immediately. By the late 1920s, the photon was an established concept in physics, a fundamental particle of nature alongside the electron and proton. But what exactly is a photon? This is where things get truly strange. A photon is not like a tiny bullet of light. It's not like a little ball flying through space. It's something much more subtle and much more bizarre than any classical object. A photon is a quantum of the electromagnetic field, a discrete excitation of a field that permeates all of space. When we say there's a photon traveling from the sun to your eye, we're really saying that the electromagnetic field has been excited in a particular way, and that excitation is propagating through space at the speed of light. This might sound like a technicality, a matter of philosophical interpretation rather than physical reality, but it's actually profound. The photon doesn't exist the way a rock or a person exists. It doesn't have a definite position in space until you measure it. It doesn't follow a definite path from source to detector. It exists as a kind of probability, a potential, a quantum of possibility that only becomes concrete when it interacts with something. The history of understanding light teaches us something important about science and about human knowledge. For centuries, the smartest people in the world were convinced they understood what light was. Newton was certain it was particles. His mathematical descriptions were elegant and predictive. Later physicists were certain it was waves. Young's experiment seemed definitive. Maxwell's beautiful theories seemed to wrap everything up in a complete package. Each generation thought the question was settled. But nature had surprises in store. The photoelectric effect and blackbody radiation showed that our understanding was incomplete. The true nature of light was stranger than anyone had guessed. And this should make us humble. If humanity's greatest geniuses were wrong about something as fundamental as light, what else might we be wrong about? What other surprises might nature have in store? The photon reminds us that the universe is not obligated to make sense to us. It is what it is, whether we can comprehend it or not. Our job as curious beings is to keep asking questions, keep doing experiments, and keep revising our understanding as we learn more. The story of light is the story of human curiosity confronting cosmic strangeness, and slowly, painfully, learning to accept that reality is far more interesting than our intuitions ever suggested. The story of the photon is far from over. The quantum strangeness of light runs deeper still. A single photon can somehow interfere with itself. Photons experience time in a way that challenges our understanding of existence, and modern physics describes the photon as one of the fundamental force carriers that hold the universe together. The more we examine this seemingly simple particle of light, the stranger it becomes. Now we arrive at the truly strange part of our story. We've seen that light behaves as a wave in some experiments and as a particle in others. Young's double-slit experiment proved light was a wave. Einstein's explanation of the photoelectric effect proved light was a particle. Both experiments are correct. Both results are reproducible, and they seem to directly contradict each other. But what happens when we try to observe this dual nature directly? What happens when we take Young's double-slit experiment, the experiment that proved light was a wave, and perform it with individual photons, one at a time? What happens when we force light to reveal its true nature by stripping away any possibility of collective wave behavior? This is one of the most famous experiments in the history of physics, and its results are so counterintuitive that even physicists who have spent their careers studying quantum mechanics find them deeply disturbing. Richard Feynman, one of the greatest physicists of the 20th century and a Nobel laureate for his work on quantum electrodynamics, said that the double-slit experiment contains the only mystery of quantum mechanics. All of the strangeness, all of the paradoxes, all of the philosophical puzzles are concentrated in this single experiment. If you can truly understand it, you understand quantum mechanics. But nobody truly understands quantum mechanics. Not really. Let me describe the experiment in detail. You have a light source that can emit individual photons, one at a time. Modern technology makes this possible. We can create sources so dim, so carefully controlled, that they release photons one by one with significant gaps between them. You have a barrier with two narrow slits, just like in Young's original experiment. And you have a detector screen behind the barrier that records where each photon lands. Unlike Young's experiment, which used photographic plates that accumulated exposure over time, modern detectors can record individual photon arrivals, marking each one with a precise location and timestamp. Now, you send photons through the apparatus, one at a time, waiting long enough between each photon that the previous one has already hit the screen before the next one is even emitted. There is never more than one photon in the apparatus at any moment. The photons cannot interact with each other. They cannot influence each other. Each photon makes its journey through the slits alone. What pattern do you expect to see on the screen after many photons have been recorded? If photons were simple particles, like tiny bullets fired at a wall with two holes, each photon would go through one slit or the other. It would travel in a straight line from the source, pass through whichever slit happened to be in its path, and continue in a straight line to the screen. Some photons would go through the left slit and land somewhere on the screen behind it. Others would go through the right slit and land somewhere behind that one. After many photons, you would expect to see two bright bands on the screen, one behind each slit. This is exactly what you would see if you fired bullets at a wall with two holes. Two piles of bullets, one behind each hole. If photons were simple waves, the wave would spread out from the source, encounter the barrier, and pass through both slits simultaneously. The two emerging waves would spread outward from the slits and overlap in the region behind the barrier. Where wave peaks met wave peaks, constructive interference would create bright regions. Where wave peaks met wave troughs, destructive interference would create dark regions. You would see the interference pattern that Young observed, alternating bright and dark bands stretching across the screen. But we're not using continuous waves, we're using individual photons, one at a time. Surely the wave explanation can't apply to single particles. Here's what actually happens. And this is where physics becomes stranger than science fiction. Each individual photon lands at a specific point on the screen, like a particle. You can see the individual dots appearing one at a time. Click. A dot appears here. Click. Another dot appears there. Each photon arrives at a single location and is detected as a single particle. So far, this matches what we'd expect from particles. But as more and more photons accumulate, the dots don't form two bands behind the slits. Instead, they gradually build up into an interference pattern. This same pattern that Young saw with continuous light, alternating bright and dark bands. Constructive and destructive interference. After 10 photons, the pattern looks random. After 100 photons, you might start to see hints of structure. After 1,000 photons, the interference pattern is clearly emerging. After millions of photons, it's unmistakable. The individual particle-like dots have collectively formed a wave-like interference pattern. This is deeply strange. Each photon is hitting the screen at a single point, like a particle. There's no ambiguity about this. The detector registers a localized event at a specific location. But the pattern they collectively form is an interference pattern, which can only be produced by waves interfering with each other. Somehow, each individual photon is interfering with itself, as if it went through both slits at once. Let me emphasize how bizarre this is. The photons are being sent one at a time. There's only ever one photon in the apparatus at any moment. There's nothing else for it to interfere with. No other photons, no other waves. Just one solitary photon making its way from source to screen. And yet, somehow, each photon's behavior is affected by the presence of both slits. Here's how we know the photon somehow senses both slits. If you close one slit, leaving only one path available, the interference pattern disappears completely. You just get a single band behind the open slit. The photons pile up in one region, exactly as bullets would. But when you open the second slit, the interference pattern returns. The photon behaves differently when two slits are available, even though it seems like any given photon should only be going through one. Think about what this means. When only one slit is open, photons can land in a certain region of the screen. But when you open a second slit, giving photons another path to that same region, fewer photons land there. Adding a second path reduces the number of arrivals. This makes no sense for particles. If bullets can reach a location through one hole, opening a second hole can only increase the number that arrive. It can never decrease them. But for photons, opening a second slit creates interference that prevents them from landing in certain locations. The standard interpretation of quantum mechanics offers an explanation, but it's an explanation that challenges everything we think we know about reality. According to quantum mechanics, before the photon hits the screen, it doesn't have a definite position. It doesn't go through the left slit or the right slit. Instead, it goes through both slits simultaneously, existing as what physicists call a superposition of possibilities. The photon is in a quantum state that includes both paths at once. Only when the photon interacts with the screen, when it's detected, does it collapse into a specific position. The mathematical object that describes this situation is called a wave function. The wave function encodes the probability of finding the photon at various locations. Before measurement, the wave function spreads out through space, passing through both slits, interfering with itself on the other side. The wave function has high values, where constructive interference occurs, and low values, where destructive interference occurs. These values determine the probability of the photon appearing at each location. When the photon is finally detected, the wave function collapses. The spread out probability distribution instantaneously concentrates to a single point. The photon appears somewhere, and the probabilities at all other locations become zero. Where it appears is random, but the probability of appearing at each location is determined by the interference pattern encoded in the wave function. This is the famous principle of superposition. Quantum particles don't have definite properties until they're measured. Before measurement, they exist in a combination of all possible states simultaneously. A photon going through a double slit is in a superposition of going through the left slit and going through the right slit. These two possibilities interfere with each other mathematically, creating the interference pattern, even though each photon ultimately lands at a single point. But wait, you might say, this is just interpretation. Maybe the photon really does go through one slit or the other, and we just don't know which one. Maybe the superposition is just a reflection of our ignorance, not a description of physical reality. If the photon really goes through both slits, can't we just watch it? Can't we put detectors at the slits and see which one the photon actually goes through? You can try. Physicists have tried many times with increasingly sophisticated equipment. And here's the strangest part of an already strange story. If you put detectors at the slits to determine which slit each photon goes through, the interference pattern disappears completely. When you know which path the photon took, it behaves like a particle, and you get two bands, one behind each slit. When you don't know which path it took, it behaves like a wave, and you get the interference pattern. Your knowledge seems to affect reality. This isn't about the detectors physically disturbing the photons, pushing them one way or another and disrupting the interference. Physicists have conducted incredibly clever experiments to rule out that mechanical explanation. They've used detectors that interact with the photons as gently as possible, barely disturbing them at all. The interference pattern still disappears. They've used setups where the witch path information could in principle be determined from the detector records, even if no one actually looks at the data. The interference pattern still disappears. They've used quantum erasers that detect a witch path information, but then destroy that information before anyone can read it. The interference pattern returns. The pattern is consistent and absolute. If it's possible, even in principle, to determine which slit the photon went through, the interference pattern disappears. The photon acts like a particle. If there's no way to determine the path, even in principle, the interference pattern appears. The photon acts like a wave. This is called the measurement problem, and it's one of the deepest mysteries in physics. The act of measurement, or even the mere possibility of measurement, seems to fundamentally change how quantum systems behave. But what counts as a measurement? Does a conscious observer need to look at the result? Does any physical interaction count as measurement? What about an interaction that records information but that no one ever examines? Physicists have been debating these questions for nearly a century, and there's still no consensus. Let me describe another experiment that illustrates this mystery even more dramatically. It's called the delayed choice experiment, first proposed by physicist John Wheeler in 1978, and subsequently performed in various forms with results that confirm its strange predictions. In this experiment, you send photons through a double slit, but you don't decide whether to measure which slit they went through until after they've already passed through the slits. You make the choice late, after the photon should have already committed to one path or both. The setup works like this. After passing through the slits, the photon travels toward a detector. The path is long enough that there's time to make a choice while the photon is in flight. Along the way, you can choose to insert a device that will tell you which slit the photon came from, or you can choose not to insert it. The key is that you make this choice after the photon has already gone through the slits, when it's part way to the detector. According to classical thinking, by the time the photon has passed through the slits, its history is fixed. It either went through the left slit or the right slit. That event is in the past. Your later choice about what to measure shouldn't be able to change what already happened. The past is the past. But that's not what the experiments show. If you choose to insert the witch path detector, the interference pattern disappears, even though the photon already passed through the slits before you made your choice. You get two bands, as if each photon went through one slit or the other like a particle. If you choose not to insert the detector, the interference pattern appears as if each photon went through both slits like a wave. Your choice, made after the photon passed the slits, determines whether the photon behaved like a wave or a particle when it went through them. This seems to suggest that the future can affect the past. Your future choice reaches backward in time to determine the photon's past behavior. This is deeply troubling to our intuitions about causality. Causes should precede effects. The past should determine the future, not the other way around. Most physicists don't interpret the delayed choice experiment as backwards causation. Instead, they say that until the photon is actually detected, it doesn't have a definite history. The photon's path through the slits, its entire trajectory from source to detector, remains undefined until a measurement is made, even if that measurement happens after the photon has traveled most of its path. History isn't fixed until it's observed. The past is as indeterminate as the future until something makes it concrete. If this interpretation disturbs you, you're in good company. It disturbed Einstein too. And it leads us to the strangest phenomenon of all in quantum mechanics. Something that Einstein famously called spooky action at a distance. You can create pairs of photons that are entangled, meaning their properties are correlated in ways that can't be explained by any classical mechanism. The correlations are stronger than any local hidden variables could produce. They seem to require some form of instantaneous connection between the photons, no matter how far apart they are. Here's how entanglement works. Through certain physical processes, you can create two photons simultaneously in a way that links their quantum states. For example, you can create two photons whose polarizations are entangled. Polarization is a property related to the direction in which the photon's electromagnetic field oscillates. It can be vertical, horizontal, or at any angle in between. For entangled photons, if you measure the polarization of one photon and find it's vertical, you instantly know that the other photon's polarization will be measured as horizontal when someone checks it. If you measure one as diagonal, the other will be anti-diagonal. The results are perfectly correlated, but here's the strange part. Before measurement, neither photon has a definite polarization. They're each in a superposition of all possible polarizations. Neither one has committed to vertical or horizontal or any other direction. It's only when you measure one that both photons collapse to definite states. And this collapse happens instantaneously, no matter how far apart the photons are. Send one photon to a laboratory on Earth, and send the other to a laboratory on Mars. When the Earth lab measures its photon and gets a result, the Mars photon instantaneously acquires the correlated property, even though it's millions of miles away. No signal could travel between them fast enough. The correlation appears immediately. Einstein hated this. He spent years arguing that quantum mechanics must be incomplete, that there must be some deeper theory with hidden variables that would explain the correlations without requiring any spooky instantaneous connections. He was convinced that the photons must have had definite polarizations all along, predetermined at the moment of their creation, and that quantum mechanics simply failed to describe these hidden properties. In 1964, physicist John Bell discovered something remarkable. He showed that Einstein's hidden variable theories would make different predictions than quantum mechanics in certain carefully designed experiments. The difference was subtle but measurable. If Einstein was right and the photons had definite properties all along, the correlations between entangled photons would obey certain mathematical inequalities, now called Bell inequalities. If quantum mechanics was right and the photons didn't have definite properties until measured, the correlations could violate these inequalities. The experiments could settle the question empirically. And when the tests were finally done, starting with Alan Aspect's groundbreaking experiments in the early 1980s and continuing to the present day with ever-increasing precision and ever more stringent controls, quantum mechanics was vindicated. The correlations between entangled photons violate Bell's inequalities. They are exactly what quantum mechanics predicts and cannot be explained by any local hidden variable theory. Einstein was wrong. In 2022, Aspect shared the Nobel Prize in Physics with John Clauser and Anton Zeilinger for their experimental work establishing the violation of Bell inequalities and the reality of quantum entanglement. The strangeness that Einstein refused to accept is now experimentally confirmed beyond reasonable doubt. This doesn't mean that entanglement can be used to send messages faster than light. When you measure your photon, you get a random result. There's no way to control what result you get. You can't encode information in the randomness. The correlation only becomes apparent when you compare measurements with your distant partner. And that comparison requires classical communication, which is limited to the speed of light. But entanglement does mean that quantum mechanics is fundamentally non-local in some sense. Two entangled photons, no matter how far apart they travel, remain connected. They share a quantum state. A measurement on one instantaneously affects what will be measured on the other. This doesn't violate relativity because no usable information is transmitted faster than light. But it does mean that quantum reality is deeply interconnected in ways that our classical intuitions completely fail to capture. So, what is a photon really? After everything we've discussed, what can we say about this quantum of light that behaves so strangely? We can say with certainty what a photon is not. A photon is not a little ball of light traveling through space with a definite position and trajectory. It's not like a tiny bullet following a predictable path from gun to target. The double slit experiment proves this. If photons were little balls, they couldn't interfere with themselves. They couldn't produce the patterns we observe. But a photon is also not a classical wave, spreading smoothly through space with a definite amplitude at every point. The photoelectric effect proves this. If photons were classical waves, their energy would depend on intensity, not frequency. Electrons be ejected gradually, not instantaneously. The experimental facts rule out classical waves just as firmly as they rule out classical particles. Instead, a photon is a quantum object, something that transcends the classical categories of wave and particle. It is described by a wave function, a mathematical object that encodes probabilities rather than certainties. The wave function spreads through space, interfering with itself, exhibiting all the properties of a wave. But when the photon interacts with the detector, when it is measured, the wave function collapses to a point, and the photon appears at a single location, exhibiting the properties of a particle. The photon doesn't have a definite position until it's measured. It doesn't travel along a definite path from source to detector. In some sense, that defies visualization. It takes all possible paths simultaneously, and these paths interfere with each other quantum mechanically. The interference determines the probability of various outcomes. But only the final outcome, when the photon is detected, is definite. Everything before that is a cloud of probability. This is deeply counterintuitive. We're used to thinking that things have definite properties whether we measure them or not. A rock sitting in a field has a definite position even if no one is looking at it. The rock doesn't spread out into a cloud of probability and only become localized when someone observes it. Our everyday experience tells us that objects are just there, with definite properties, independent of observation. But photons are different. Electrons are different. Atoms are different. All quantum objects are different. Their properties are genuinely undefined until measurement brings them into existence. The measurement doesn't just reveal a pre-existing property, it creates the property. Before measurement, the property simply doesn't exist in any definite form. Some physicists are comfortable with this picture. They accept that quantum mechanics is just how the world works at the fundamental level, And our intuitions, which evolved to handle the macroscopic classical world of rocks and trees and predators, simply don't apply at the quantum scale. Quantum reality is different from classical reality. We should update our intuitions rather than insisting the universe conform to them. Other physicists find this deeply unsatisfying. They search for alternative interpretations of quantum mechanics that might preserve some notion of underlying reality, some sense that things have definite properties even when we're not looking. The many worlds interpretation developed by Hugh Everett in the 1950s says that the wave function never actually collapses. Instead, whenever a quantum measurement is made, the universe splits into multiple branches, each corresponding to a different possible outcome. In one branch, the photon went through the left slit. In another branch, it went through the right slit. Both outcomes actually occur, but in different universes that no longer interact with each other. We only experience one branch, which is why we perceive a single outcome. But all outcomes happen somewhere in the vast multiverse. The pilot wave interpretation, also called Bohmian mechanics after physicist David Bohm, says that particles do have definite positions at all times, but they're guided by a wave that spreads through space and tells them how to move. In this picture, a photon does go through one slit or the other, following a definite trajectory, but the guiding wave goes through both slits, and it's the wave that creates the interference pattern by steering particles away from certain regions and toward others. These alternative interpretations make exactly the same predictions as standard quantum mechanics for all experiments we've done so far. They're not experimentally distinguishable with current technology. They're more about philosophical comfort, about finding a picture of reality we can accept, than about scientific necessity. But the fact that physicists continue to debate them nearly a century after quantum mechanics reached its mature form shows how unsettling the quantum nature of photons remains. One thing is certain. The photon is not a simple particle, it's not a simple wave. It's a quantum object that transcends both categories. It exhibits wave-like behavior when propagating through space, and particle-like behavior when interacting with matter. Both aspects are essential to understanding what it is. Neither aspect alone captures the full picture. Attempting to force the photon into one category or the other leads to contradictions and paradoxes. This wave-particle duality is not unique to photons. It applies to all quantum objects. Electrons, protons, neutrons, even whole atoms exhibit both wave-like and particle-like properties, depending on how you measure them. In 1923, French physicist Louis de Broglie proposed that all matter has wave properties, with a wavelength inversely proportional to its momentum. Heavy, fast-moving objects have very short wavelengths, too short to detect. But light particles moving slowly have longer wavelengths that can be measured. This prediction was confirmed experimentally in 1927 when Clinton Davison and Lester Germer observed electron diffraction. They fired electrons at a crystal surface and observed an interference pattern, just as you would expect from waves diffracting off the regular arrangement of atoms. The wave nature of matter is now a well-established fact, used routinely in electron microscopes that achieve resolution far beyond what light microscopes can provide. But photons were the first quantum objects to be identified. They hold a special place in the history of quantum mechanics. Light was the first thing that refused to fit into classical categories, the first phenomenon that demanded a fundamentally new way of thinking about reality. And because light is so easy to produce, manipulate, and detect, photons remain the ideal system for exploring quantum phenomena. Much of what we know about quantum mechanics was first learned by studying photons. Most of the classic experiments that reveal quantum strangeness use light. The quantum nature of photons has practical applications that affect daily life. Lasers depend on the quantum properties of photons. The light from a laser is coherent, meaning all the photons are in the same quantum state, oscillating in phase with each other. This coherence, impossible to achieve with classical light sources, enables everything from barcode scanners to fiber optic communication to delicate surgical procedures. Quantum cryptography uses the fact that measuring a quantum system inevitably disturbs it to create communication channels that are fundamentally secure against eavesdropping. If someone tries to intercept the photons carrying your quantum encrypted message, they'll disturb the quantum states in detectable ways. Any eavesdropping attempt announces itself. The laws of physics guarantee security in a way no classical encryption scheme can match. Quantum computing uses superposition and entanglement to perform certain calculations exponentially faster than classical computers. A classical bit is either 0 or 1. A quantum bit, or qubit, can be in a superposition of 0 and 1 simultaneously. This allows quantum computers to explore many possibilities in parallel. Photons are one of the leading candidates for qubit hardware because they're easy to manipulate, maintain their quantum states for long times, and can be transmitted over long distances through optical fibers. But even with all these practical applications, the fundamental mystery remains. What is a photon really? Not what does it do, not how do we describe it mathematically, not what can we build with it, but what is it? What kind of thing exists in a superposition of states? What kind of object has no definite properties until measured? What kind of reality underlies the wave function? These questions have occupied the greatest minds in physics for a century, and they remain unanswered. The photon, this seemingly simple quantum of light, contains depths of mystery that we have not yet plumbed. We can calculate its behavior with extraordinary precision. We can predict experimental outcomes to 10 decimal places, but we still don't know what the photon really is. Perhaps this is a limitation of human intuition rather than a limitation of physics. Our brains evolved to model the macroscopic world, to track prey and avoid predators and remember where fruit trees grow. We didn't evolve to visualize quantum phenomena. Maybe the quantum world is simply unvisualizable, inherently beyond the reach of human imagination, accessible only through mathematics. Or perhaps future insights will bring new understanding. Perhaps some physicist not yet born will find a way to make sense of quantum mechanics that satisfies our craving for a comprehensible reality. Perhaps the wave function describes something real that we simply haven't learned to see yet. For now, we live with the mystery. The photon exists. It behaves in ways we can precisely describe and accurately predict. But what it is, in itself, remains one of the deepest questions in science. And that mystery continues into an even stranger realm. One where photons experience something we take for granted in radically different ways than we do. Time itself behaves strangely for photons. And that strangeness reveals something profound about the nature of existence. Now let's explore another aspect of the photon that's just as strange as its quantum nature, perhaps even stranger. This aspect comes not from quantum mechanics, but from Einstein's special theory of relativity, published in 1905, the same miraculous year he explained the photoelectric effect and introduced the world to light quanta. And it concerns how photons experience space and time. Actually, that phrasing is already misleading. It assumes that photons experience space and time the way we do, just perhaps in different amounts or at different rates, but that's not right at all. In a very real sense, photons don't experience time. Period. To understand why, and to grasp just how profound this statement is, we need to understand what Einstein's special relativity tells us about the nature of space, time, and the speed of light. Before Einstein, physicists assumed that space and time were absolute. Space was like an infinite stage on which events occurred, unchanging and identical for all observers. Time was like a cosmic clock, ticking away at the same rate everywhere, for everyone, regardless of their motion or location. Newton had built his entire system of mechanics on these assumptions, and it had worked brilliantly for over 2 centuries. Planets orbited the sun according to Newton's equations. Cannonballs followed predictable arcs. The universe seemed to operate like a giant clockwork mechanism, with absolute space and absolute time as its unchanging framework. Einstein demolished this picture completely. Special relativity is built on 2 fundamental principles, both of which seem reasonable on their own but lead to revolutionary consequences when combined. The first principle is that the laws of physics are the same for all observers moving at constant velocity relative to each other. This seems almost obvious. If you're on a smoothly moving train with the windows covered, you can play pool or pour coffee or drop a ball just as easily as if you were standing still on solid ground. The ball falls straight down. The coffee stays in the cup. There's no experiment you can do inside the train to determine whether you're moving or stationary, as long as the motion is uniform. Galileo recognized this principle 4 centuries ago. It's called the principle of relativity. The second principle is more surprising, more counterintuitive, and ultimately more consequential. It states that the speed of light in vacuum is the same for all observers, regardless of how they're moving or how the light source is moving. Light always travels at exactly 299,792 kilometers per second in empty space. Not approximately, exactly. This speed is so fundamental to the structure of reality that physicists give it its own symbol, the letter C, from the Latin word celeritas, meaning swiftness. At first, this second principle seems impossible, even absurd. It violates everything we know about how velocities combine in everyday life. Imagine you're standing on a train platform, and a train passes by at 100 kilometers per hour. A passenger on the train throws a ball forward at 20 kilometers per hour relative to the train. How fast is the ball moving relative to you? Simple arithmetic says 120 kilometers per hour. The velocities add up. This is just common sense, and it matches our everyday experience perfectly. Now, imagine you're standing still, and a photon passes you at the speed of light. Your friend is in a spaceship moving in the same direction as the photon at half the speed of light. Surely, from your friend's perspective, the photon should appear to be moving at only half its original speed, right? That's how velocities normally combine. That's how everything else in the universe works. But light doesn't work that way. No matter how fast your friend is moving, no matter in what direction, light still passes them at exactly the same speed. C. If they're moving toward a light source, the light still reaches them at C. If they're moving away from it, the light still reaches them at C. If they're moving at 99% of the speed of light in the same direction as a light beam, that light beam still passes them at c, not at 1% of c. The speed of light is absolute, constant, the same for everyone in every circumstance. This experimental fact had been established before Einstein, most famously by the Michelson-Morley experiment in 1887, which tried to measure Earth's motion through the supposed luminiferous ether by comparing the speed of light in different directions. The experiment found no difference whatsoever. Light traveled at the same speed regardless of Earth's motion through space. This result baffled physicists for nearly 2 decades until Einstein provided the explanation. Einstein realized that for the speed of light to be constant for all observers, space and time themselves must be different from what everyone had assumed. They can't be fixed, unchanging backgrounds against which events occur. Instead, space and time must adjust themselves, must stretch and compress, must behave differently for different observers, all to ensure that light always travels a c relative to everyone who measures it. This leads to the famous consequences of special relativity, time dilation and length contraction. These aren't optical illusions or measurement errors. They're fundamental features of reality, built into the fabric of space-time itself. Time dilation means the time passes at different rates for observers moving at different velocities relative to each other. If you're moving relative to me, I'll observe your clock running slower than mine. Your heartbeat will be slower. Your thoughts will unfold more slowly. Everything about you will proceed at a reduced rate from my perspective. And here's the strange part. You'll observe exactly the same thing about me. From your perspective, I'm the one who's moving and my clock is the one running slow. This isn't a contradiction. It's a consequence of the fact that there's no absolute frame of reference. Neither of us is objectively stationary. We're both equally entitled to claim that we're at rest, and the other is moving. The amount of time dilation depends on relative velocity according to a precise mathematical formula derived from the constancy of light speed. At everyday speeds, the effect is negligible. Even a jet airplane moving at 1,000 kilometers per hour experiences time dilation of only a few nanoseconds per flight. You'd need atomic clocks of extraordinary precision to detect it, though such experiments have been done and confirm the predictions exactly. But as speeds approach the speed of light, time dilation becomes dramatic. At 90% of the speed of light, time passes at only about 44% of its normal rate. A clock moving at this speed would tick less than half as fast as a stationary clock. At 99% of the speed of light, time passes at only about 14% of its normal rate. At 99.9%, about 4.5%. The faster you move, the more slowly time passes for you. This has been confirmed experimentally many times with high-energy particles. Muons, subatomic particles created when cosmic rays strike the upper atmosphere, have a very short lifetime, about 2.2 microseconds when at rest. Given their altitude of creation and their speed, they should decay long before reaching Earth's surface. Most of them should disintegrate in the upper atmosphere, but muons are moving at close to the speed of light, and time passes more slowly for them. From their perspective, they live their normal brief lives. From our perspective, they live much longer, long enough to reach our ground-based detectors in large numbers. The muon experiment is a beautiful real-world demonstration that time dilation is not just a theoretical prediction, but a measurable fact of nature. GPS satellites, which orbit Earth at high speeds, have their onboard clocks corrected for time dilation effects. Without these corrections, the clocks would drift out of synchronization with ground-based clocks by about 7 microseconds per day due to their orbital velocity. This would cause GPS position calculations to be wrong by several kilometers. The fact that your phone can pinpoint your location to within a few meters is a daily practical confirmation of Einstein's theory. Length contraction is the spatial counterpart of time dilation. Objects appear shorter in the direction of their motion. If a spaceship flies past you at 90% of the speed of light, it appears compressed along its direction of travel, physically shorter than it would be at rest. From the perspective of people on the spaceship, their vessel is its normal length, but your measuring sticks appear compressed. Both perspectives are correct within their respective frames of reference. There is no absolute length any more than there is absolute time. Now here comes the critical question. The question that reveals something profound about the nature of photons. What happens at the speed of light itself? What happens as velocity approaches c and time dilation approaches infinity? The formula for time dilation includes a factor called the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who discovered it before Einstein. This factor depends on velocity in a specific way. As velocity approaches c, the Lorentz factor approaches infinity. Time dilation becomes infinite. For an object traveling at exactly the speed of light, time stops completely. But wait, doesn't this mean that nothing can actually travel at the speed of light? And you'd be right. For objects with mass, as any massive object speeds up, its kinetic energy increases. Near the speed of light, this energy increases dramatically. To accelerate a massive object to exactly the speed of light would require infinite energy, which is obviously impossible to supply. That's why you, me, spaceships, planets, and anything else with mass can never reach the speed of light, no matter how much energy we expend. We can get arbitrarily close, with enough energy, reaching 99%, 99.9%, 99.99%, approaching but never reaching that ultimate speed limit. The speed of light is a barrier that massive objects can approach, but never cross. Photons are fundamentally different. Photons have no mass. Zero. Exactly zero. This changes everything. Photons don't have to accelerate to the speed of light from some lower velocity. They don't exist at any speed other than c. From the moment of their creation to the instant of their absorption, photons travel at exactly the speed of light. They are born at c, they travel at c, and they die at c. There's no other option. A photon that isn't moving at the speed of light simply doesn't exist. Speed c isn't a choice for photons. It's a defining characteristic of their existence. This leads to a profound and almost incomprehensible consequence. From the photon's own perspective, no time passes, ever, at all. A photon emitted from a star in a distant galaxy, traveling across the cosmos for 10 billion years before striking a telescope on Earth, experiences no duration whatsoever during this immense journey. From its own frame of reference, if we can even speak of such a thing for a photon, the moment of emission and the moment of absorption are simultaneous. They are the same instant. The photon's entire existence from creation to destruction happens in a single timeless moment of zero duration. Let me try to make this more concrete, though truly concrete visualization may be impossible for creatures like us who are trapped in the flow of time. Imagine a photon emitted from the surface of the sun. From our perspective here on Earth, that photon travels for about 8 minutes and 20 seconds before reaching us. We can trace its journey. At 1 minute, it's roughly 18 million kilometers from the sun. At 4 minutes, it's halfway to Earth. At 8 minutes, it's almost here. The journey has duration. It has stages. It unfolds through time. But from the photon's perspective, none of this intermediate travel exists. The moment it leaves the sun's surface is identical to the moment it strikes your retina. There is no gap between these events. There is no journey. There is no during. The photon doesn't experience traveling through space. It doesn't experience being at any intermediate point. It doesn't experience waiting to arrive. For the photon, departure and arrival are the same event, occurring at the same instant. This also means that from the photon's perspective, distances contract to zero. Length contraction at the speed of light is complete. The entire 93 million miles between the sun and Earth collapses to nothing. The sun and your eye are, from the photon's point of view, at the same location. Not close together, not nearly touching, literally at the same point in space. Now, physicists will tell you that it's not strictly correct to talk about a photon's frame of reference. The mathematics of special relativity is formulated for observers moving at less than the speed of light, and the equations produce undefined results exactly at c. Dividing by zero yields infinity, and physics doesn't work with infinities in this direct way. Saying that time stops for a photon is a limiting case, an extrapolation from what happens as velocity approaches c, not something that can be rigorously defined within the theory's formal structure. But this mathematical technicality doesn't diminish the strangeness of the situation. It's certainly true that as you move faster and faster, getting closer and closer to the speed of light, time passes more and more slowly for you. The limit of this process, as velocity approaches c, is that time passage approaches zero. Photons are at this limit. They exist at the boundary of what's physically possible. They live, if that word can be used, at the edge of causality itself. This has fascinating implications for how we think about photons crossing the universe. We talk about light from distant galaxies traveling for billions of years to reach us. The Andromeda galaxy is about 2.5 million light years away. Light leaving Andromeda today will reach Earth in 2.5 million years. Light reaching us today from Andromeda left that galaxy when our ancestors were barely using stone tools. But from the photon's perspective, no time has passed. Those photons, ancient as they seem to us, have experienced no duration at all. They're as fresh as the moment they were created. Because for them, it is still the moment they were created. The entire 2.5 million year journey is, from their point of view, instantaneous. The cosmic microwave background radiation is even more extreme. This faint glow that fills the universe is the afterglow of the Big Bang, light emitted when the cosmos was only about 380,000 years old, when the hot plasma that filled the universe cooled, enough to become transparent. This light has been traveling toward us for nearly 13.8 billion years. It's the oldest light we can observe, a relic from the earliest epoch we can see. Yet from the photon's own perspective, no time has elapsed since the moment of emission. Those photons have experienced no duration at all since they left the primordial plasma. They don't know they're ancient messengers from the dawn of time. They don't know they've crossed the entire observable universe. For them, the moment of emission in the hot plasma of the early universe and the moment of absorption in a radio telescope on Earth are the same instant, separated by nothing. There's something almost poetic about this. The photons that carry information from the earliest moments of cosmic history, from the first stars that ignited, from distant galaxies at the edge of the observable universe, all experience their entire existence as instantaneous. They're messengers from the past that don't know they're messengers. They carry no memory of their journey because they experience no journey. They simply exist, timelessly, at the boundary between emission and absorption. This timeless quality of photons relates to their quantum properties in interesting ways. In quantum field theory, antimatter can be viewed as matter traveling backward in time. This is called the Feynman-Stueckelberg interpretation. A positron, the antiparticle of the electron, can be mathematically described as an electron moving backward through time. The equations work out exactly the same either way, but photons are their own antiparticles. A photon is identical to an antiphoton. There is no distinct antiphoton, no partner particle with opposite charge. The photon is its own mirror image in this sense, and this fits beautifully with the idea that photons experience no time. If there's no time direction for a photon, if past and future are the same instant, then the distinction between forward and backward in time becomes meaningless. A particle that doesn't experience time cannot be distinguished from its time-reversed counterpart. Let me explore another aspect of photons and relativity. Why does light travel at this particular speed, 299,792 kilometers per second? Why not faster? Why not slower? What's special about this number? The answer turns out to be profound. The speed of light isn't really about light. It's a fundamental property of space-time itself. The speed c is the speed at which information and causality can propagate through the universe. It's the maximum speed at which any influence can travel from one event to another. It's the conversion factor between space and time, revealing that they're aspects of a single entity called space-time. In a universe without any light, without any electromagnetic fields at all, this speed would still exist. It would still be the cosmic speed limit. It just happened that electromagnetic waves, including visible light, travel at this maximum possible speed. Any massless particle travels at this speed. Gravitational waves, ripples in space-time itself, predicted by general relativity and first detected in 2015, also travel at exactly c. Maxwell discovered this speed through his equations of electromagnetism, finding that electromagnetic waves would propagate at a velocity determined by the permittivity and permeability of free space. He calculated the number and realized it matched the measured speed of light. But Maxwell didn't create this speed by inventing electromagnetic theory. The speed was already built into the fabric of reality. Light just happens to travel at the universe's speed limit. Why is there a maximum speed at all? Why can't things travel as fast as they want? This gets into deep questions about causality and the logical consistency of the universe. If there were no speed limit, cause and effect would break down. It would become possible, at least in principle, to send information backward in time, and that would create paradoxes. You could send a message to your past self telling yourself not to send the message. The logical contradiction would make the universe incoherent. The existence of a maximum speed, combined with the relativity of simultaneity and the structure of space-time, preserves causality. Events can influence other events, but only in a consistent temporal order that all observers agree upon, at least for the question of what can cause what. The photon, traveling at this maximum speed, lives at the boundary of causality. It travels along what physicists call the light cone, the boundary between events that can causally influence each other and events that cannot. Picture a space-time diagram, a graph with time on the vertical axis and space on the horizontal axis. You're at the origin, the present moment. Your past is below you on the diagram. Your future is above you. Space extends to the left and right. Now draw two diagonal lines through your location, angled at 45 degrees, one going up and to the right, one going up and to the left. These represent the paths that light beams would take, traveling away from you into the future. Draw similar lines going down and to the sides, representing light beams that could have reached you from the past. These diagonal lines form two cones, opening upward into the future and downward into the past. Everything inside your past light cone, below and between the downward opening diagonals, could have affected you. Information from those events had time to reach you traveling at light speed or slower. Everything inside your future light cone, above and between the upward opening diagonals, can be affected by you. Your actions now can influence those future events because signals have time to reach them. Everything outside both cones, the regions to the sides, is causally disconnected from your present moment. Events there happen too far away and too recently for any signal to have reached you, even traveling at light speed. Events there in the future are too far away for any signal from you to reach them in time. You cannot influence them, and they cannot have influenced you. They exist in what physicists call elsewhere, neither your past nor your future in any causal sense. Photons travel along the light cones themselves. They're at the edge of what's causally possible. They define the boundary between influence and isolation. They connect events that are on the precise margin of being able to affect each other. In a profound sense, photons define the structure of space-time, tracing out the scaffolding that separates causally connected from causally disconnected regions of the universe. This brings us to another strange property of photons, one that connects their relativistic nature to their quantum nature in subtle ways. Because photons travel at the maximum speed, because time doesn't pass for them because they're massless, photons of a given frequency are identical no matter where you are or how you're moving. A photon with a wavelength of 500 nanometers, green light, is the same object whether observed from a stationary laboratory or from a spaceship traveling at 99% of C. Its frequency might appear different to different observers. If you're moving toward a light source, the light appears blue shifted with higher frequency and shorter wavelength. If you're moving away, it appears red shifted with lower frequency and longer wavelength. This is the Doppler effect, familiar from the changing pitch of a passing siren, extended to light, but it's still the same photon. The photon itself hasn't changed. What's changed is the relationship between the photon and the observer. The photon's intrinsic properties, its masslessness and its speed, remain identical. Only its apparent frequency shifts. In contrast, massive particles look genuinely different depending on your reference frame. An electron moving slowly has different observable properties than an electron moving quickly. Its kinetic energy is different. Its de Broglie wavelength is different. Its time dilation factor is different. You can meaningfully distinguish a fast electron from a slow electron, but you cannot speed up or slow down a photon. You can only observe it from different frames of reference, which changes its apparent frequency but not its fundamental nature. Every photon travels at exactly c. You can change your relationship to the photon. You cannot change the photon's relationship to space-time. This constancy has interesting consequences for cosmology. The cosmic microwave background radiation was emitted when the universe was about 380,000 years old. When hot plasma cooled enough to form neutral atoms and become transparent to light. At that time, the radiation was mostly visible light, with a thermal spectrum corresponding to a temperature of about 3,000 degrees Kelvin, similar to the reddish glow of a relatively cool star. But since then, the universe has expanded by a factor of about 1,100. Space itself has stretched, carrying galaxies apart and stretching the wavelength of light traveling through it. The cosmic microwave background photons have been stretched by the same factor. What was visible light is now microwave radiation, with wavelengths measured in millimeters instead of hundreds of nanometers. The temperature of the radiation has dropped from 3,000 degrees to about 2.7 degrees above absolute zero. Yet these are the same photons. They haven't changed their intrinsic nature. They've been redshifted by the expansion of space, but they still travel at sea, still experience no time, still carry information about the epoch of their creation. The universe has grown around them, stretching their wavelengths like marks on an expanding balloon. But the photons themselves remain fundamentally what they always were. The interplay between quantum mechanics and relativity, between the particle wave nature of photons and their timeless existence at the speed of light, remains one of the deepest subjects in physics. Quantum field theory, which combines quantum mechanics with special relativity, provides our best description of photons. In this framework, the photon is an excitation of the electromagnetic field, a quantum ripple in a field that permeates all of space-time. But there are still profound puzzles at the intersection of quantum mechanics and gravity that we haven't solved. General relativity, Einstein's masterwork theory of gravity completed in 1915, describes gravity as the curvature of space-time. Massive objects bend the fabric of space-time around them, and other objects follow the curved paths through this warped geometry, which we perceive as gravitational attraction. Planets orbit stars not because invisible forces pull them inward, but because they're following the straightest possible path through space-time that the sun's mass has curved. Photons, though massless, also follow these curved paths. Light bends around massive objects like stars and galaxies. This effect, called gravitational lensing, was first observed during a solar eclipse in 1919, confirming Einstein's prediction and making him an international celebrity. The sun's mass bends starlight passing close to it, slightly shifting the apparent positions of stars seen near the solar disk. Today, gravitational lensing is a powerful tool in astronomy. Massive galaxy clusters bend light from more distant galaxies behind them, sometimes creating multiple images of the same distant object, sometimes stretching it into arcs, sometimes magnifying it to make otherwise invisible objects detectable. The warping of space-time by mass affects photons just as it affects everything else, but we don't have a complete quantum theory of gravity. We don't know how to describe gravity and space-time at the quantum level. General relativity describes gravity as smooth geometry. Quantum mechanics describes reality as fundamentally granular, made of discrete quanta. Reconciling these two pictures is one of the great unsolved problems in physics. When we do figure it out, our understanding of photons might change. The fundamental structure of space-time might be different than we currently think, and photons, as probes of that structure, might reveal new properties we can't currently anticipate. For now, though, we have a picture of the photon that's already strange enough to occupy a lifetime of contemplation. A massless quantum of the electromagnetic field. A particle that is also a wave. An entity traveling at the maximum speed allowed by the structure of space-time. A messenger that crosses billions of light years without experiencing a moment of duration. A definer of causality, tracing out the light cones that separate influence from isolation. The photon exists at the boundary of everything, at the boundary between particle and wave, at the boundary of time, experiencing none, at the boundary of causality, connecting events that can just barely affect each other, at the boundary of our understanding, revealing that reality is far stranger than our everyday intuitions suggest. And yet, for all its strangeness, the photon is also familiar. It's the light by which you read these words. It's the warmth of the sun on your face. It's the glow of every star in the night sky. It's the signal carrying your phone calls through fiber optic cables. It's everywhere, always. This quantum of light that experiences no time and defines the structure of reality. But there's still more to understand. How do photons fit into the complete picture of modern physics? How do they serve as carriers of the electromagnetic force? And what questions remain unanswered about this most fundamental and most mysterious entity? The answers reveal that the photon sits at the very heart of reality itself. We've explored the quantum nature of photons and their strange relationship with time. We've seen how they exist as both waves and particles, how they interfere with themselves, how they experience no duration despite traveling across billions of light years, how entangled pairs maintain correlations that no classical theory can explain. Now it's time to put everything together and see how modern physics describes what a photon truly is at the deepest level we currently understand. This brings us to quantum electrodynamics, abbreviated QED, the theory that describes how light and matter interact at the most fundamental level. QED is not just another physical theory, it is arguably the crown jewel of 20th century physics, a mathematical framework of such precision and predictive power that it stands as one of humanity's greatest intellectual achievements. QED was developed in the late 1940s, primarily by three physicists working independently. Richard Feynman in the United States, Julian Schwinger also in the United States, and Shinichiro Tomonaga in Japan. All three arrived at equivalent formulations of the theory through different mathematical approaches. They shared the 1965 Nobel Prize in Physics for their work, recognition that QED represented a fundamental advance in our understanding of nature. The precision of QED's predictions is almost incomprehensible. The theory matches experiments to an accuracy of better than 1 part in a trillion. To put this in perspective, if you could measure the distance from New York to Los Angeles with the same relative precision, you would be off by less than the width of a human hair. No other theory in any branch of science comes close to this level of agreement between prediction and measurement. QED is, by this measure, the most successful scientific theory ever developed. In QED, the photon takes on a ME role far more fundamental than simply being a particle of light. The photon is the carrier of the electromagnetic force itself. Every time two charged particles interact, every time they attract or repel each other, every time they exchange energy or momentum through electromagnetic means, they do so by exchanging photons. When an electron repels another electron, it's because they're trading photons back and forth. One electron emits a photon, the other electron absorbs it, and the momentum transferred by the photon pushes them apart. When a proton attracts an electron, binding them together into a hydrogen atom, that attraction is mediated by photon exchange. The entire electromagnetic force, one of the four fundamental forces of nature, is carried by photons. This might seem strange. When you rub a balloon on your hair and it sticks to a wall, you don't see photons flying between the balloon and the wall. When a magnet attracts a piece of iron, there's no visible light connecting them. The photons that carry the electromagnetic force between ordinary objects are not the same as the photons we see with our eyes. These force-carrying photons are called virtual photons, and they're fundamentally different from the real photons that travel through space and register on our retinas. A real photon is one that exists independently, propagating through space from a source to a destination until it interacts with something. The photons streaming from the sun that warm your skin are real photons. They were emitted by hot plasma in the solar atmosphere, traveled 93 million miles through space, and were absorbed by molecules in your body. The photons emitted by your reading lamp that let you see this text are real photons. They can be detected, counted, absorbed, and measured. They carry energy and information from one place to another. Virtual photons, on the other hand, exist only briefly, as intermediaries in interactions between charged particles. They cannot be directly detected as independent entities. They don't travel freely through space in any ordinary sense. They pop into existence when one charged particle accelerates or shakes, carry the influence of that disturbance to another charged particle, and then vanish. Their existence is fleeting, constrained by the Heisenberg uncertainty principle to timescales so short that they can never be isolated and observed. The concept of virtual particles might sound like a mathematical trick, a computational convenience rather than a description of physical reality. And in some ways, this is a matter of philosophical interpretation rather than empirical fact. You can't capture a virtual photon in a bottle and study it in isolation. Virtual photons appear only in the intermediate steps of calculations, never in final observable outcomes. But virtual particles are essential for making QED's incredibly accurate predictions. Without them, the calculations don't work. The numbers don't come out right. Virtual photons are as real as anything else in quantum field theory, which is to say their ultimate metaphysical status remains debatable, but their effects are undeniable and precisely measured. Richard Feynman developed a powerful visual and computational technique for working with quantum electrodynamics. He represented particle interactions with simple diagrams that have become icons of modern physics, now universally called Feynman diagrams. These diagrams are not just illustrations. They're a rigorous mathematical notation that encodes the rules for calculating what happens when particles interact. In Feynman diagrams, matter particles like electrons are shown as straight lines, with arrows indicating their direction through time. Photons are shown as wavy lines. When two electrons interact, you draw them as straight lines coming together from the past, connected by a wavy photon line, and then separating toward the future. The photon carries momentum and energy from one electron to the other, causing them to change direction, which we observe as repulsion. The simplest Feynman diagram for electron-electron scattering shows just one photon exchanged. But QED allows for more complex possibilities, and here's where the theory becomes both mathematically challenging and physically profound. Before the exchanged photon reaches the second electron, it might briefly transform into an electron-positron pair, a particle and its antiparticle appearing momentarily from the photon's energy, then annihilating back into a photon that continues on its way. Or the photon might emit and reabsorb another photon during its brief existence. Or the electrons themselves might emit and reabsorb photons before and after the main exchange. These additional processes are represented by additional loops and lines in the Feynman diagrams. There are infinitely many possible diagrams for any given interaction. An electron approaching another electron might exchange one photon, or two photons, or three. Each photon might spawn temporary electron-positron pairs. Each electron might emit virtual photons that it later reabsorbs. The possibilities multiply without end. Fortunately, not all diagrams contribute equally to the final answer. More complex diagrams, with more loops and more virtual particles, contribute less and less. The simplest diagrams give the dominant contribution. The next simplest give small corrections. Extremely complex diagrams contribute corrections so tiny they can be ignored for any practical purpose. Calculating all these contributions, even just the dominant ones, was one of the great technical challenges of 20th century physics. The mathematics could be nightmarishly complex. Early attempts to calculate even simple processes produced infinite answers, obviously nonsensical results that suggested something was deeply wrong with the theory. The breakthrough came when Feynman, Schwinger, and Tomonaga independently developed techniques to handle these infinities, a process called renormalization. The details are technical, but the key insight was that certain infinite quantities could be absorbed into the definitions of physical quantities like the electron's mass and charge. Once this was done properly, the remaining calculations gave finite, sensible, and extraordinarily accurate predictions. The magnetic moment of the electron provides the most famous example of QED's precision. The electron behaves like a tiny magnet, with a strength characterized by a number called the G factor. Simple quantum mechanics predicts this G factor should be exactly 2. But QED predicts small corrections from all those virtual photons and virtual electron-positron pairs that constantly surround the electron. When you calculate these corrections to many decimal places, a process that requires evaluating thousands of Feynman diagrams, you get a prediction for the electron's G factor. This prediction has been calculated to 12 decimal places, and it matches the experimentally measured value exactly to every decimal place we can measure. This agreement between theory and experiment is one of the most stunning achievements in the history of science. In the framework of QED, what exactly is a photon? It's an excitation of the electromagnetic field. The electromagnetic field permeates all of space. At every point in the universe, there exists a value for the electric field and a value for the magnetic field, united in the single electromagnetic field that Maxwell discovered in the 1860s. In classical physics, these fields are smooth and continuous, able to take any value at any point, varying smoothly from place to place and moment to moment. But in quantum mechanics, everything is quantized. Energy comes in discrete packets, angular momentum comes in discrete units, And fields, it turns out, are also quantized. The electromagnetic field is not smooth and continuous at the fundamental level. It's made up of discrete quanta, individual packets of excitation that cannot be subdivided. Each quantum of the electromagnetic field is a photon. Think of it like this. Imagine a calm pond, its surface perfectly still. The surface of the pond represents the electromagnetic field in its lowest energy state, the vacuum state with no photons present. The field exists everywhere, just as the pond surface extends across the whole pond, but nothing is happening. No disturbances are propagating. Now drop a stone into the pond. Ripples spread outward across the surface. These ripples are like photons, discrete excitations of the pond surface that propagate away from their source. Each ripple carries energy. Each ripple has a wavelength and a frequency. Each ripple eventually dissipates when it reaches the shore or interacts with something else in the water. In quantum field theory, the electromagnetic field is like this pond, and photons are the waves that propagate across it. When we say that an atom emits a photon, we mean that an electron in the atom drops to a lower energy level, and the energy difference is released as an excitation of the electromagnetic field. This excitation propagates away at the speed of light, carrying the released energy with it. When we say the photon is absorbed by another atom, we mean that the excitation reaches another electron and transfers its energy, causing that electron to jump to a higher level. The photon, as a distinct entity, exists only between emission and absorption. This field picture helps explain some of the strange quantum behaviors we explored earlier. Why does a photon seem to go through both slits in the double slit experiment? Because the photon isn't a tiny ball traveling along a specific path. It's an excitation of a field that spreads through space like a wave. The field goes through both slits, interferes with itself on the other side, and only when the excitation interacts with the detector, only when it is absorbed, does it manifest at a specific point. The wave-like propagation and the particle-like detection are both aspects of how excitations of quantum fields behave. Why doesn't a photon experience time? Because there's an excitation propagating at the maximum possible speed. At that speed, according to special relativity, time dilation becomes infinite. The photon exists, in some sense, outside of time's flow. It is created and absorbed in what, from any perspective we could define for it, is a single, timeless instant. QED also explains why photons have no mass, and this explanation reveals deep connections to the mathematical structure of the theory. In quantum field theory, mass is associated with the energy of a field even when there's no excitation propagating. A massive particle is an excitation of a field that has this rest energy, this energy present even when the particle is stationary. An electron at rest has energy equal to its mass times the speed of light squared, Einstein's famous equation. This rest energy comes from properties of the electron field. A massless particle is an excitation of a field that has no rest energy. The electromagnetic field has this property. There's no minimum energy required to create an excitation. Photons can have any energy, from the tiniest radio wave photon to the highest energy gamma ray, and there's no lower limit. This is why photons are massless. The masslessness of photons has profound consequences for the electromagnetic force. Because photons are massless, they can mediate a force that extends to infinite range. The electromagnetic force between two charged particles decreases with distance, falling off as the inverse square of the separation, but it never reaches zero. Even across billions of light years, two charged particles exert some electromagnetic influence on each other, mediated by virtual photons. The force becomes incredibly weak at large distances, but it never vanishes entirely. Compare this to the weak nuclear force, one of the other fundamental forces of nature. The weak force is responsible for certain types of radioactive decay and plays a crucial role in nuclear fusion within stars. It's mediated by particles called W and Z bosons, but these bosons are massive, roughly 80 to 90 times the mass of a proton. Because W and Z bosons are massive, they can only exist for an extraordinarily brief time before quantum uncertainty demands they vanish. They can only travel an extraordinarily short distance during this time, roughly 0.1% of the diameter of a proton. Beyond that distance, the weak force is essentially zero. Two particles separated by more than this tiny range simply don't interact through the weak force at all. The masslessness of the photon gives electromagnetism its infinite reach. The massiveness of the W and Z bosons confines the weak force to subatomic scales. Mass determines range in the quantum world of force-carrying particles. The masslessness of the photon is intimately connected to a deep symmetry of the electromagnetic field called gauge symmetry. This symmetry is one of the most important concepts in modern physics, underlying not just electromagnetism, but all the fundamental forces. Gauge symmetry says that you can transform the mathematical description of the electromagnetic field in certain ways without changing any physical observable. You can add gradients to the electromagnetic potential, shift the phase of charged particle wave functions in corresponding ways, and all the physics comes out identical. Nothing you could measure would be different. This might sound like a mere mathematical curiosity, a quirk of the equations rather than a deep physical principle. But gauge symmetry has profound implications. It requires the force carrier to be massless. If the photon had any mass whatsoever, gauge symmetry would be broken, and the mathematical structure of electromagnetism would collapse. The same principle applies to the other forces. The gluons that carry the strong nuclear force are also massless, preserving the gauge symmetry of quantum chromodynamics. The graviton, the hypothetical carrier of gravity, would also be massless if it exists. Gauge symmetry and massless force carriers go hand in hand. But wait, didn't I just say that the W and Z bosons are massive? How can the weak force have massive carriers if gauge symmetry requires masslessness? This puzzle drove much of particle physics research in the 1960s and 70s. The resolution involves a subtle mechanism called spontaneous symmetry breaking. Discovered theoretically by several physicists, including Peter Higgs, after whom the Higgs boson is named. In spontaneous symmetry breaking, the underlying equations of a theory possess a symmetry, but the lowest energy state of the system does not. The weak force is fundamentally unified with electromagnetism in a single electroweak force. At high energies, like those in the early universe or in the most powerful particle accelerators, this unity is manifest. The photon and the W and Z bosons are all part of the same mathematical structure, all massless carriers of the unified electroweak force. But as the universe cooled after the Big Bang, symmetry breaking occurred. The Higgs field, which permeates all space, settled into a non-zero value. This non-zero value gave mass to the W and Z bosons, while leaving the photon massless. The symmetry that unified them was broken, hidden, though it still exists in the underlying equations. This is why we perceive electromagnetism and the weak force as different today. The photon remains massless, giving electromagnetism its infinite range and preserving its gauge symmetry in the low-energy world we inhabit. The W and Z bosons acquired mass, confining the weak force to subatomic scales and hiding the underlying unity. The photon is thus not just a carrier of the electromagnetic force, it's a window into the deep structure of the standard model of particle physics, into the symmetries that underlie all of physics. Understanding the photon helps us understand why the forces of nature are the way they are, why some have infinite range and others are confined to the tiniest scales. And as we saw earlier, entangled photons reveal another deep truth about quantum reality. The non-local correlations between entangled pairs, correlations that Bell's theorem proves cannot arise from any local hidden variables, show us that the quantum world is interconnected in ways that defy classical intuition. QED fully accounts for these correlations, predicting them with the same extraordinary precision it brings to everything else. Entanglement isn't a mystery within QED, it's a natural consequence of how quantum fields behave. So, what does all of this tell us about what a photon really is? Let me attempt a synthesis. A photon is an elementary particle, one of the fundamental building blocks of nature, according to the standard model. It has zero mass and always travels at the speed of light. It carries energy proportional to its frequency and momentum, proportional to its energy divided by the speed of light. It has a property called spin, an intrinsic angular momentum with a value of 1 in the natural units physicists use. This spin manifests as polarization, with two possible states corresponding to left and right circular polarization. A photon is also a quantum of the electromagnetic field, a discrete excitation of a field that permeates all of space-time. The electromagnetic field is not made of photons the way a wall is made of bricks. Rather, photons are disturbances in the field, localized packets of energy and momentum that propagate at light speed. The field exists everywhere, even in empty space. Photons are what happens when the field is excited above its ground state. A photon is the carrier of the electromagnetic force. Every electromagnetic interaction, from the binding of electrons to atomic nuclei, to the repulsion of like charges, to the radiation of energy from hot objects, is mediated by photons. Real photons carry electromagnetic energy from place to place. Virtual photons transmit the electromagnetic force between charged particles, even though they cannot be directly observed. A photon exhibits wave-particle duality. In some experiments, it behaves like a wave, spreading through space, interfering with itself, diffracting around obstacles, producing patterns that only waves can produce. In other experiments, it behaves like a particle, hitting detectors at specific points, transferring discrete amounts of energy, registering as individual clicks in photomultipliers. Neither picture alone captures what a photon is. Both are aspects of a deeper quantum reality that transcends classical categories entirely. A photon experiences no time. Traveling at the universal speed limit with infinite time dilation, a photon's entire existence from creation to destruction happens in a single instant from its own perspective. Photons don't age. They don't experience duration. They cross billions of light years without a moment passing. They exist at the boundary of time itself. A photon can be entangled with other photons, maintaining non-local correlations across arbitrary distances that no classical mechanism can explain. Space doesn't separate entangled photons the way our intuitions insist it should. All of these properties are strange. Every single one challenges intuitions built from everyday experience with macroscopic objects. But every single one is supported by experiment, by measurement, by the most precise observations humans have ever conducted. The photon is strange because nature is strange at the fundamental level. Quantum reality doesn't behave the way our brains, evolved for tracking predators and finding food in the African savanna, expect things to behave. Particles don't have definite properties until measured. Effects can be correlated across space without any signal traveling between them. Time itself varies depending on motion and vanishes entirely at light speed. The photon forces us to confront these truths because it's one of the simplest quantum systems, one of the easiest to produce and detect and manipulate, one of the most thoroughly studied entities in all of physics. And yet it remains, in many ways, deeply mysterious. So the next time you see light, whether it's the sun warming your face on a summer afternoon, a star twinkling in the night sky, the glow of your phone screen, or just the lamp on your desk, remember what you're actually looking at. Those are photons. Massless quanta of the electromagnetic field. Entities traveling at the maximum speed the universe allows. Messengers that cross cosmic distances without experiencing a single moment of time. Carriers of the force that holds atoms together and makes chemistry possible. Particles that are also waves. Excitations of a field that fills all of space-time. And somehow, these strange entities let you see. They carry information about the world to your eyes, where they're absorbed by rhodopsin molecules in your retina, triggering conformational changes that produce electrical signals, signals that travel through your optic nerve to your brain, where they're processed into the experience of vision. The same photons that are so quantum mechanical, so relativistic, so profoundly weird, are also the foundation of everything you've ever seen, every face you've recognized, every sunset you've watched, every word you've read. That's what a photon really is. A messenger from the universe, carrying energy and information across the cosmos at the maximum possible speed. A quantum of the electromagnetic field, the fundamental medium through which charged particles interact. A window into the deeper structures of physics, revealing symmetries and unifications that we're only beginning to understand. A puzzle that humanity's greatest minds have worked on for over a century and still haven't completely solved. Light seems so ordinary. It's always there, illuminating the world, making life possible. But when you probe its nature with experiments, when you think carefully about what the results mean, you find something extraordinary. Light is made of photons, and photons are among the strangest things that exist. Einstein, who first proposed that light came in quanta, spent the rest of his life troubled by the implications. He never fully accepted quantum mechanics. He was convinced there must be some deeper level of reality that would make the quantum world sensible and deterministic. But experiment after experiment has shown that quantum mechanics, including its description of photons, is correct as far as we can measure. Perhaps future physics will resolve some of these mysteries. Perhaps a successful theory of quantum gravity will reveal the photon to be something even stranger than we currently understand. Perhaps we'll discover that our current theories are approximations to deeper truths we haven't glimpsed. Physics has surprised us before, and it will likely surprise us again. But for now, we have the photon as we know it. A massless, timeless quantum that carries light across the universe. One of the best understood entities in all of physics, and yet one that remains genuinely mysterious. Both of these statements are true simultaneously, and perhaps that's fitting for a particle that exists in superposition. The photon teaches us humility about our place in the cosmos. It shows us that the universe operates according to principles that transcend human intuition, that reality at its foundations is stranger than we ever imagined, and yet still describable by mathematics with extraordinary precision. It shows us that the simplest things, like a beam of light, can contain depths of mystery that centuries of investigation have only begun to explore. Sleep well tonight under the stars. Every point of light you see is sending photons toward you, particles of ancient light that have traveled for years or centuries or millennia to reach your eye. And from their perspective, that journey took no time at all. They carry no memory of the voyage because they experienced no voyage. They're as fresh as the instant of their creation. The starlight that reaches you tonight is a gift from the cosmos, strange and beautiful and waiting to be understood. And the next time you turn on a lamp or step into sunlight, remember that you're surrounded by one of the deepest mysteries in physics, hiding in plain sight, as it always has been. Since the first photon raced away from the first star at the beginning of time,